Hello, colleagues. Today we have a new technical talk, and today our speaker is Lasse Peters, who is a PhD candidate at the Department of Cognitive Robotics at Delft University of Technology, advised by Javier Alonso Mora and Laura Ferranti. His research interests lie in combining methods from optimal control, game theory, and reinforcement learning to design safe and efficient strategies for multi-agent interaction. Before coming to Delft, he was full-time research scholar in the photogrammetry and robotics lab of Cyril Staknis, sorry if I'm not pronouncing it correctly, and a visiting research scholar at UC Berkeley, the hybrid system lab of Claire Tomlin. He received a master's in mechatronics and a bachelor's in mechanical engineering from TU Hamburg, Germany in 2020 and 2017 respectively. So let's start.
Yeah, thank you for the kind introduction. So yeah, my name is Lasse Peters, and today's talk is on contingency games for multi-agent interaction. And this work has been conducted together with Andrea Baischi, Ji-Yuan Chu, David Fridovich Kyle, Forrest Lane, Laura Ferranti, and Javier Alonso Mora. Now, as the title reveals, this talk is about multi-agent problems. And let me focus my slides here. And these problems, they are quite common all over the place in the real world. So whenever we want to move our robot outside of some cage, we usually will encounter some humans. For example, if we want to navigate this intersection, as the red car is doing here, then we need to, in order to do that safely and efficiently, we need to negotiate our actions and coordinate them with other agents, such as the pedestrians and cyclists here in the scene. Now, if you've ever tried to get close to campus on a busy day in the Netherlands, then you will be aware that this can be quite challenging because when there's many agents around, it can also become quite difficult to coordinate your actions with them. And if you can't properly predict how your actions will affect others, and you can't predict how other people will behave, which is tightly dependent on your own actions, then you may get into inefficient or even unsafe situations. Or an even more extreme example is shown here, where there's a pedestrian suddenly crossing the road, and then in the middle of the road, they decide to turn around and get back to the other side. And so if we put ourselves into the shoes of the driver in this last scene, of course, now we've seen the scenario and we know what's going to happen. But if we first encountered this scenario, we would drive along this road and potentially we would see the pedestrian for the first time now. And well, we've maybe seen them just a little bit now. And so we've seen them running to the left. So it seems quite likely that they continue in that direction. And so we would plan to pass on the right. But as an experienced driver, we may be aware, maybe we've seen them turn their head around or communicate to someone on the right side of the street. And so we would be aware that this is not the only thing that they may do. We are aware that they may suddenly turn around, and therefore we also have to consider another option in which we have to brake and then pass them on the left. And as an experienced driver, we will know that we will also get some more information in the near future. So all we need to do is to commit to an action that remains safe now and that can be continued safely and efficiently once we get more information. And so these three examples, and in particular the last one, highlight three important aspects of real-world multi-agent reasoning. So the first is that the actions of agents are highly interdependent, meaning that the things that I can do safely and efficiently depend on what everyone else is doing, and we can't simply predict what others do and then plan our action accordingly, because other people's action, other agents' actions will depend on us. And then furthermore, there's an abundance of uncertainty. So in robotics, we're already familiar with all the sources of uncertainty from perception and localization, but in particular in these multi-agent settings, there is uncertainty about the intentions of other players. So what do they even want to do in this scene? And finally, there's this notion of planning contingencies, which means that we will usually get some more information later, and we need to make plans in a conditional way that allows us to make use of this future information. And contingency games, which is the key focus of this talk, is a method for formalizing this kind of reasoning by proposing a mathematical model for planning contingencies through the lens of dynamic game theory. Now, since the key element of this method really is dynamic game theory, I want to quickly review some of the basics of that theory, irrespective of any sort of notion of contingencies at first. And so we'll use this last example that we've seen with the pedestrian running over the road as a running example throughout this talk, which you can see kind of abstracted on the right. Imagine that this purple car is an autonomous robot, and there's the pink human, and they need to interact, and we try to cast this problem as a game. Now, if we want to cast it as a game, we will get a system of coupled optimization problem in which each of the players with index I, where we have index, so the index may take the values H for the human or R for the robot. Each of these agents have their own optimization problem in which they choose their own trajectory, tau I, and they choose this trajectory, which is the sequence of states and control inputs, to minimize their own respective cost. And this cost encodes their objective. And this cost in general will depend not only on their own trajectory, but it may depend on the trajectory of everyone else. So we will use this not I notation here to denote all of the players except for player I. And then beyond the cost, their behavior will usually, or this trajectory optimization process for a single player will be also guided by constraints. And these constraints can encode aspects like dynamics, but also collision avoidance or other aspects of the environment, lane keeping, and so on. And in general, these constraints may depend on the decisions on the trajectories of others. So the feasible set for every player in this dynamic game is a function of what others do, which is commonly the case, for example, in collision avoidance. And so when we find a trajectory in the arc minimizers of each of these optimization problems, which are solved in this coupled way, then we end up with a generalized Nash equilibrium, which intuitively means that we have a trajectory, or at a generalized Nash equilibrium, no player has a unilateral incentive to deviate to another trajectory, another feasible trajectory. And so when we use this kind of paradigm for autonomous decision-making, then from the egocentric perspective of the purple vehicle, we can cast our environment description as this kind of game. Then we solve it, and the solution of it gives us both a game-theoretic prediction of the human, which is tightly coupled with our corresponding optimal response, so the equilibrium response for the robot. And in practice, as you would do with model predictive control, we can apply this in a receding horizon fashion, in which case we would call this model predictive gameplay. So at every planning interval, we always take our current state and sort of an environment model, and then we solve this problem repeatedly to update our plan with the best information that we have right now. Now, of course, you may have noticed that I've made some implicit assumptions about a bunch of information that we just happen to have. And the most important assumption that kind of makes it difficult to directly apply this kind of game-theoretic reasoning in real-world settings for egocentric planning is that we often don't know the intents of other players a priori, which will be a key challenge that we focus on during this talk. And so in the example before, this kind of intent, which is encoded in the cost, maybe the unknown goal position of the human. We don't know, do they want to reach a goal on the left or do they want to reach a goal on the right? And there may be this, if we have these unknown design elements in the game, a common approach to deal with it is that we can aggregate all of these unknown parameters into parameter vector theta, and then we can use Bayesian inference or approximate Bayesian inference to maintain a belief over these parameters. And there's been various works that have done this in the past using, for example, particle filters or uncentered Kalman filters. And so in the end, we end up with a distribution over game parameters. So to say, a distribution over games and or intents, and therefore a distribution over behavior. And the question is, how can we use this belief distribution, this belief of intents for planning? And to that end, there's kind of two established techniques. So the simplest thing that you could do immediately is that, okay, let's consider we have two options: the human goes left or the human goes right. So this is their goal positions, and we've maintained a belief over these two options. And we have a slightly higher belief that the human goes right. One thing that we may do is that we just discard all but the most likely option. And so we make a point estimate of our belief by, for example, making the maximum a posteriori estimate. So we simply look for the theta, which maximizes this belief. And with this estimate, we can then just plug it into a certainty equivalent game. So we just sort of pretend our belief knows about this alternative universe in which the human wants to go to the left. But in this formulation, for the sake of planning, we just choose the most likely hypothesis, and we just completely discard everything else and solve a certainty equivalent game. So we would conclude the human goes to the right, and we can just pass them on the left. We still solve a game, but ignoring this belief. That's, of course, easy, and a key benefit of this is that we can directly use the established solvers, the established game solvers, to use this kind of approach directly. And that's certainly a nice benefit. But the problem is that by discarding a substantial portion of the probability mass, we may get into unsafe behavior. So if the human does indeed plan to go to the left, which may happen with up to 50% probability if we just take the most likely option, we are on a direct path for collision. And so really, the goal should be to not to find a method that uses this entire distribution for planning. And so another popular method that has been explored in various flavors in different works is to plan an expectation. And so in that formulation, we get a slightly different optimization problem for the robot, where now the robot optimizes their trajectory tau r to minimize the expected cost over the entire distribution of beliefs. Sorry, over the entire distribution of intents. So the different parameters that are here are the intent parameters. And so they are effectively playing against a distribution of human trajectory, each of which is computed under a different intent hypothesis. And they are also required to remain feasible with respect to all of these human variants. And so while the robot plans their trajectory to minimize the expected cost, they play against k versions of the human, where k is the number of hypotheses. So the human with intent theta has their own optimization problem. So if we have the options left and right, we will generate one ghost version of the human that has the intent left, and they only care about the version of the world in which they go left. And then we also have another human that goes right. And so we effectively here end up with a 3-player game. The robot plays against two versions of the human, minimizing their expected cost, minimizing its expected cost in interaction with both of the humans. And each of the humans only sees one version of the world under their intent. So they only play against the robot. And so what's nice about this is that we use the entire belief. And so we get a substantially more safe behavior because we account for uncertainty. However, a disadvantage is that, as you can see on the right, because we also get the constraints from all of these hypotheses over the entire planning horizon, we may get overly conservative behavior because now the entire roadway appears blocked and there seems to be no way for us to make progress. So we just have to come to a full stop. And since we don't consider the fact that we will get more information in the future, this may become overly conservative. And so the contingency games framework that we will introduce next seeks to bridge the gap between these two approaches by accounting for future information in a tractable manner. So if we look at our running example again, if we were to cast this problem as a contingency game, the key idea is that we will plan with the current uncertainty that we have in our belief, but we anticipate that we will have certainty in the future at a future time TB, which we call the branching time. And so what this means on a high level is that when we have our initial belief, we first make a single plan up to TB, up to this future point of certainty, that has to consider all of the hypotheses and minimizes the cost and expectation. And then starting from TB, we have separate conditional plans, each of which is conditioned on the possible outcomes that we may observe at TB. And since this is still cast as a game, this conditional plan is tightly coupled with the different human predictions under each of the intents. And so if we look at this, if we formalize this approach, it looks very similar to the planning and expectation framework with a minor difference. So the robot now minimizes the expected cost over all of the hypotheses as before, but importantly, we endow the robot with a separate trajectory for each hypothesis. So the robot is allowed to take a separate trajectory for hypothesis left and right of the human. So there's one for when the human goes left, then we would plan to go on the right, and vice versa. And then these are not optimized only to minimize the cost, but they also have to respect the constraints under each hypothesis. So so each of them sees their own constraints under the corresponding intent. But since the human can't, since the robot can't, this plan, of course, would be inconsistent, right? So if we look at this again, we now have two different actions that we want to take. And there's this plan isn't actionable because we effectively plan against these different versions of the human. And so the contingency aspect is added by enforcing that all of the control inputs up to the branching time must be consistent across the different plans, which enforces that we cannot commit to any action that would render us unsafe. We cannot commit to any action that cannot be continued safely or efficiently under any possible outcome observed after TB. So after TB, the two plans can deviate, but before they must be consistent across all hypotheses. And then the human is as before. We have a different version of the human for each possible intent, and they only care about their version of the world. So for the human, there is no difference. So we have these two ghost humans that interact with the conditional plan of the robot now. And since this is still a game, our conditional plan is tightly coupled with these human predictions. And so in application, we would then use the trajectory for the robot as a conditional plan. And the trajectories for the human, you can see them as sort of multimodal predictions that are game-theoretic predictions of the human. Okay, so that sort of concludes the mathematical formulation. Now, to build some intuition, we've built a little widget to play around with the parameters of the solver. And the first parameter that's quite instructive to look at is to vary the belief. And so if we vary the belief, then we can see that the contingency games generate plans that balance the cost of the different hypotheses according to their likelihood. For example, if we think that it's quite likely that the human goes to the right, meaning that the probability of them going to the left is quite low, as indicated by the current slider position, then we would mostly bias our plan to the left so that we can smoothly pass the human on the left, which is kind of our nominal prediction. But should the human instead decide to go to the left, then we still have a backup plan, which allows us to feasibly turn to the right, with its cost being traded off according to the likelihood. And importantly, as I've said earlier, the trunk will always be, because this entire conditional plan is optimized jointly, the robot cannot choose any actions before TB, which doesn't allow it. So it must be feasible for all outcomes, and it cannot choose any action which may render it, which doesn't leave it with a feasible plan after TB. Now, the second parameter that we may want to vary is the branching time. And when we vary this parameter, then we can observe that for earlier branching, we get more optimistic plans, which allow the robot to commit to either of the plans early. Whereas when branching happens very late, meaning that we get more information about the humans very late, we end up with more conservative behavior. And in particular, at the extremes of this parameter, at extreme values of this parameter, we recover the existing methods as a special case. So if the branching time is equal to the planning horizon, then we end up with a single plan for the robot over the entire horizon, and we just recover the planning expectation approach. And if we allow the branching time to be 0, then it means that the robot has immediate certainty, and we effectively end up with the certainty equivalent plans. Okay. So to summarize what I've just shown you in this widget is that with contingency plans, we get this additional tunable parameter of the branching time, which we can tune according to the information gain dynamics, or we can also choose it more rigorously based on reachability analysis. And there's some nice work on that in the context of single player sort of non-game contingency planning. And with this parameter, we get this entire spectrum of contingency games, where at the extreme values of the parameters, we have point estimates on the one extreme and planning and expectation on the other. Okay, that's a question. I think we have time for a question.
Yeah, thanks. This is really interesting. One question I have is there a reason we would set TB to be greater than the planning like frequency? So if we're operating in this MPC-like world, could we not say we're going to just plan for both eventualities until I have to replan again?
Yeah, so that's kind of the minimum value, I would say, and that's a very good question. So if you set TB to equal to 1, then it's very similar to what people do in POMDP planning when they do QMDP type approaches, where you have certainty at the immediate next time step. But that may be also overly optimistic, because it effectively means you think that you will have full certainty in one step, but in practice, your belief updater may be slower. So like even after taking 3, 4, 5 observations, you may still have some minimum, some sort of remaining uncertainty. So in general, the branching time will be a function of the speed of your belief updater and not only control rate.
Thank you.
Sorry, yeah, also one more question, if we are starting to ask question right now. So about this belief, here on the image, we can see that, yeah, we have quite discrete values like left and right, but in reality, it's like the whole continuous spectrum of possible intentions and how to incorporate this continuum, to be honest.
Yeah, so that's also a good question. So this method indeed is tailored towards settings with finite support, and in practice, I would envision this to be used, for example, in unison with the uncentered Kalman filter, where sort of the support points would be the sigma points of the Kalman filter. But within the planning, we can only consider discrete options. That's correct.
So it's like the approach is narrowed down towards a very like small number of possible intents, like left, right, slow, or fast moving.
Yeah, at least a finite number. So I have a slide in the end, so we have some nice preliminary results on parallelizing the computation over these hypotheses, so that at least if you have many of them, but you have multiple cores, you can parallelize the computation in a nice way. But in the end, they need to be finite. So yeah, there's no immediate way in this framework. There may be an extension of this work that also deals with continuous uncertainty, but here we assume a finite support. And the discretization may happen through sampling from a continuous distribution or other kind of discretization.
Can we, for example, understand as different intents, for example, some goals, like goals on the road, like XY positions?
Yes, so I think common types of intents could be the preferred lane of a player on a highway, or their target road on an intersection, or their goal position, or I mean different sort of nominal travel velocity, something like that. Any aspect that we may have uncertainty about. But of course there would, and I think that's an interesting question, is how do you generate these kind of candidate support points that you should even care about, because maybe some of these uncertainties don't even matter, like knowing whether someone I don't know what is an example, but if you have two goal positions that are both on the left of the road, it probably doesn't really matter which of the two they want to go to, and having some sort of model order reduction that groups them into a small number of things that you should really discern would probably be necessary for a real-world deployment.
I see. Thank you.
Okay. So yeah, let's... we have another question. I think I have to move on. Let's try to have some more questions at the end. I just don't want to run out of time, because there's still some stuff to discuss.
Okay.
So let's move on to solving contingency games. So far we've discussed this two-player toy example with two hypotheses, but now for solving, let's consider the n-player contingency game setting. So if we want to solve that, we can do that by finding trajectories that satisfy the KKT system of this, so the first order necessary conditions of this coupled optimization problem. And if you are familiar with constraint optimization in the single player case, so outside of the context of games, then you'll be very familiar. It's quite symmetric to what we have here. What we do is that we set up the Lagrangian for every player, which for the robot is structured as follows. So we have the expected cost, and because, as discussed, the support is finite, we can express it as a sum. So it's simply the weighted sum of the costs under each of the hypotheses weighted by the belief. And then we also have this term for the constraints. So a Lagrange multiplier times the constraints, where we have represented this this constraint calligraphic K with the algebraic representation H. And then since we have the robot, we also have the contingency constraint, which only appears once, which it forces that all the control inputs are consistent up to TB. And then for the human, so for the robot, we've assigned index 1, and the opponents, which may now be more than one human, they are all all the players with index larger than 1. For each of them, we have a version under a different intent parameter theta. Each of them have their own Lagrangian, which again comprises of their cost minus lambda times their constraints. And since they are not planning in any contingent fashion, they just care about their version of the world. There's no notion of expectation or a notion of a contingency constraint. Now, with these two Lagrangians, or with these list of Lagrangians, one for each player, we then can assemble the KKT system, which for this contingency game, so for a generalized Nash game, is simply the stacked KKT conditions for the individual optimization problems. So for the first, for each of the player, we get 5 conditions. First, we have the gradient of the Lagrangian must be 0 with respect to the primal decision variables. Then we have primal feasibility, meaning that the constraints must be satisfied and the duals must be non-negative. And whenever the primal constraints are positives or inactive, the duals must be 0 and vice versa. And then for the contingency constraint, for the robot, we also have the contingency constraint, for which, because it's an equality constraint, there are no complementarity conditions. And so if we attempt to solve this KKT system, we can use a tool called mixed complementarity problems, or MCPs for short, which is annoyingly close to MPC, but they're not the same. Now, a mixed complementarity problem in its general form asks the following question. Given a function f mapping from Rd to Rd and the vector of lower bounds L and upper bounds U in the same space, find vector Z in Rd so that f evaluated at Z complements the condition that Z is between the bounds. And that's a very compact notation for the following requirement. We require that for each of the elements J, one of the 3 conditions holds. And either Zj is at the lower bound here, in which case we require that the jth element of f is greater or equal to 0, or Z is between the bounds, Zj is between the bounds, in which case we require f to be at the root, or Zj is at the upper bound, in which case we allow f to be smaller or equal to 0. So really you can think of this as root finding with some extra steps. Namely, whenever Z is between the bounds, we exactly want to find a root, and whenever Z is at one of the bounds, we allow f to deviate to either side. And while this doesn't seem to be a very handy or practical sort of tool that you should care about in practice, the nice thing is that you can solve a lot of relevant problems in this framework, including the KKT systems for optimization and games. And so if we stare at this formulation for long enough, you can see that we can encode the entire KKT system from the previous slide and exactly in this framework by aggregating the problem data as shown below. Now, of course, I will spare you going over all of these blocks, but we can at least verify some of it to get some intuition. For example, the first block here, which corresponds to the primal decision variables, is aligned with the gradient of the Lagrangian. And for those blocks, we have set the bounds to be plus and minus infinity. And this means that these values, they will always be between the bounds. So we exactly require f for these elements to be at the root, which exactly encodes the stationarity condition from the previous slide. And similarly, you can verify all of the other blocks in this problem data below, to get to see that these indeed encode the same problem. Okay, so with this in place, the nice thing is that if f is sparse, if the gradient of f is sparse, then modern MCP solvers, in particular, I'd like to highlight the Path Solver by Stephen Dirkse and co-authors, can find solutions to these mixed complementarity problems quite rapidly. And the nice thing is that, especially in this multi-agent settings where dynamics of different players typically are separable, meaning that we have our own vehicle and someone else has their own dynamics, this sparsity is quite pronounced. And so even though the worst case complexity of solving these problems is quite bad, in practice it's not all that scary. So what do I mean by solving these problems quite rapidly? For example, for a 3-player game with 25 time steps and 2 hypotheses, so that's over, I think, 5 seconds of prediction, we would synthesize a mixed complementarity problem with about 3,000 decision variables, but we can still solve this within 35 milliseconds in our fairly unoptimized research implementation of this method. Okay, so that concludes the section on how we can solve these kinds of methods, these kinds of problems synthesized by contingency games. Now, next, I'd like to show you some quantitative results. And in this evaluation, we compare our contingency game solver against non-contingent multi-hypothesis methods. And so with that, I mean the planning and expectation baseline that I've shown you earlier. So the key difference is that we want to study now to which extent does accounting for this earlier information gain allow us to improve over the baseline. And the first kind of evaluation that we did is an open loop to do this evaluation irrespective of any replanning behavior, but we will get to evaluation with replanning in a minute. So we did this evaluation on 2 kinds of examples. The first is the pedestrian crossing the road with unknown sort of intention of which side they want to go. This is the example we've exercised throughout this talk. And then we've also evaluated it on this highway example where there's a pedestrian with unknown lane changing and velocity preferences in front. And the average sort of overall observation that we get by running this method for 25 different branching times, each of which we simulate at 70 different randomly sampled initial states, is that across all configurations and initial states, we can reduce the cost over the baseline quite a bit. And if we look at exactly how this cost is distributed as a function of the branching time, then we observe that for late branching, where the branching time equals the planning horizon, of course the gap is 0 because the methods are exactly equivalent. But then as we reduce the branching time, the gap is more and more pronounced in this open loop evaluation. And another thing that we may want to do is to look at how this gap is distributed spatially, and for that we have visualized the relative cost gap between the 2 methods at these 4 highlighted slices of the branching time. And so that you can see on the right. And from this, you can see that the cost gap is particularly pronounced at around 40 or even more percent reduced cost when we get information sufficiently early. So like here for TB equals 5, so within 5 seconds. And in particular, when the human is still in the middle of the road, because then getting some more information before we reach their position allows us to find a more efficient plan. And that, of course, in practice, you would say, okay, but replanning fixes some of these issues. And so the question then is, how much can the baseline kind of improve also by replanning? And therefore, we redid this evaluation in a setting where we allow both methods to replan at the branching time. And so in the second evaluation, we see a slightly different picture. Now, as before, for late branching, we still have no gap, which is clear because the 2 methods are equivalent. We just get information so late that all the interesting part of the interaction has already played out. And for very early branching, in contrast to the previous evaluation, now the gap is also quite small. So here's about 4%. And that effectively means, well, if you're able to replan very quickly, and you reach certainty very quickly, so your belief update is very fast, then even though the baseline produces a poor plan, which maybe breaks quite a bit because it's very conservative, this conservative behavior will only be applied for a short time. And so it doesn't affect the overall cost all that much, because very quickly you will have certainty, and then you can continue with a certainty equivalent solution. And so you should really care about this in this intermediate range, where you get information a bit later, but not too late to still make use of it. So when your belief updater is in a regime where where the belief dynamics are characterized by branching times between 5 and 11 in this example, you would see a pronounced advantage of contingency planning. And to get an idea where some of this inefficiency of the baseline is coming from, if we look at the replanning dynamics here, we see that for the baseline, initially it had planned to break because it was unsure in which direction the human wants to go. And then when it gets more information at the branching time, it has to significantly correct its plan and will then see, okay, the human indeed wants to go to the left, so I will need to replan and I can go to the right. And so this initial breaking is what costs it quite a bit. Whereas for the contingency plan, at the initial time, we have already created a conditional plan. And then by the time we reach the branching time, we can simply select between the two plans that we've computed earlier. Okay, so that concludes the main portion of the talk. As a conclusion, I'd like to also give a brief outlook of some possible next steps. And the first of this is in going beyond intent uncertainty. So far, we've looked at cases where the uncertainty comes from the intents of other players, so the cost function effectively. But in many settings in the reality, there's other types of uncertainties that we may care about. For example, imagine that you're encountering a pedestrian that's pushing a bike, and your perception pipeline may not be sure, is this now a pedestrian, or is it a biker, or is it some other semantic class? And depending on this semantic class, which is quite naturally categorical, we would be uncertain about what they can do. So we are uncertain about their feasible set. We are uncertain about their dynamics. And the fact that this can be quite important became quite clear also in the incident at Uber a couple of years ago, where they say that their perception pipeline was unsure about the classification, the semantic class of this pedestrian, and this effectively resulted in their method being unable to make consistent and meaningful predictions. And so I think that in this setting, contingency games can also provide a good way of planning with this entire distribution without becoming overly conservative. And a second direction is something that I've quickly mentioned earlier, which is that we could also speed up the computation of contingency solutions by parallelizing them over the different hypotheses. And for that, we already have some preliminary results, which are currently under review at CDC. And so that paper is not specifically about contingency games, but about a broader class of stochastic games, but it readily applies to the framework that we've discussed here. And through this operator splitting technique, if you have many threads, you can effectively parallelize this problem into several smaller games, which you can then iteratively combine in an ADMM fashion. Okay, so that concludes my talk. So to summarize, contingency games are a model for strategic interaction, which allow a robot to consider the full distribution of other agents' intents while anticipating intent certainty in the near future. Now, if you want to learn more about this, we've also set up a project website, at the link below. And there we've also put this widget that I've shown you earlier if you want to play around with it more and build some more intuition. Thanks. I think now we should have still some time for questions.
Thank you, Lasse. Let's thank the speaker for this talk, first of all. And now probably we have additional questions. Colleagues?
Hello, Lasse. Yeah, thanks for the talk. This is really nice. I have a question about, is there a general framework to decide the branching time, the TB? I think, suppose it's a more interactive case, right? Suppose there is oncoming agents, then that branching time become more critical, right? If we decide that branching time is too late, then we might not be able to, right, react to some uncertainties. But if we decide that too early, then maybe, like you said, we have more variances. So is there a framework or study on deciding the TB?
Yeah, that's a very good question. So in general, so there's some nice work from Andrea Baischi, who has used reachability analysis on the belief data to get a conservative estimate of TB. So effectively, you can kind of think about what are the worst case observations that I could get. So what is the sort of worst case time for me to get certainty? And so over approximating TB isn't all that, I mean, just leaves you with more conservative behavior, but at least it is safe, right? So, and this reachability approach is probably the most rigorous approach that I'm aware of. In practice, most of the existing works, they still treat it as a sort of tunable parameter that you kind of, set manually, which I agree is not too satisfying. But I think that this reachability approach is pretty interesting because effectively it allows you to make a conservative estimate of TB, and then in practice you don't get the worst case observation, and so your TB will likely reduce much faster, your branching time.
Yeah, reachability makes sense here. So does that mean TB is fixed for the whole contention horizon for this agents, or TB is still computer live with every invocation? It will be updated since the reachability might be different.
So I think the TB should be updated at every time step, and if your analysis is correct, it should. And there's no new uncertainty arising because of new agents entering the scene, then it should effectively reduce by 1 at every planning interval. So whenever you move one time step, it should reduce by 1, right? But in practice, of course, there will be some uncertainty added every time step because of maybe localization or new agents entering the scene, in which case, usually I think it will be, there would be a module that's kind of mapping your current belief to a branching time, which heuristically may be closely related to the initial entropy. And then, you plan with that. I think, and that's something that we're currently exploring also for an extension of this work, is that in practice you could probably get away with fixing the TB at some nominal value, which is effectively closely related to your average, your nominal performance of the belief data. But I would expect it to be not 0, so you shouldn't expect to sort of be immediately certain, but also not 25. So I think it's nice to have this additional parameter to tune it according to your experience with your perception pipeline.
Yeah, thank you.
Also a short question from my side. Did you try to evaluate your proposal on like large-scale data sets for prediction and planning, like Waymo, something like that?
No, we haven't yet. That's still on the bucket list. But yeah, I'm also curious to see. The main thing is that, especially with this game-theoretic method, it's pretty important that, or it is least strictly more interesting if you can get some kind of response out of the other agents instead of evaluating on a static data set, for which the options are quite limited. But we've also just recently looked at the nocturne simulator from Facebook. And I think that, yeah, that's certainly a good direction. I would be very interested to see that.
Yeah, also some like planning challenges. Like currently we have like machine learning based new plan, and probably some others. Also the question from my side, do you consider the knowledge of context map information as the input for your model?
Yeah, yes. So yeah, we do. So in the same, so I think that the input requirements, you can see them very similar to model predictive control, right? So like you assume that there are some pre-processing step that gives you sort of your constraints and the positions of others. The difference to the model predictive control setting is that in the MPC setting, we would expect some trajectory prediction model to give us the future position of other players, whereas here we need some belief over intents, and these predictions are generated jointly within this game-theoretic framework.
I see. Thanks.
Yeah, I might have one more question. I think in several months ago, there was another talk about the IOQ games. It's still a theoretical game. Yeah, it's a game theory, computing that. So what's the difference with the contingency game compared to the IOQ game? Probably know that works on TV.
Yes. Yeah, so David has also been on this paper. So yeah, I've also contributed to the IQ games framework. So IQ games, you can effectively see it as a solver for, well, it's an approximation to feedback games, and it doesn't make any specific assumptions about the particular formulation. Importantly, IQ games in the way that we've originally proposed it does not support any constraints. So in that sense, it's different because it doesn't solve for generalized Nash. And also doesn't support inequality or equality constraints, so beyond dynamics. So it would be a bit difficult to cast a contingency game, like solve a contingency game directly with the IQ games algorithm, simply because we couldn't express the all of these elements exactly. So we can't, for example, encode the contingency constraint in that framework. In the end, there's probably a variant where you can apply that algorithm, but you should really see the IQ games algorithm as sort of it takes more the role of the path solver that I've shown here. So the contingency games framework is not a specific algorithm; it's a problem formulation to cast the environment in this game-theoretic way. And then we solve it with the path solver, but you could solve it with any other MCP solver. For example, there's also L games from Stanford or some other works specifically tailored towards games. And in the feedback version, you could also use an IAQ games-like approach.
Oh, I see. So you are saying for the IOQ game, we can only have the dynamics as the non-convex constraint. We could not have any other constraints. But for the contingency game, it's more general framework that supports general inequality constraints. So I think that's actual benefits. Maybe on the downside of this is maybe IOQ game is more efficient than solving the contingency games. I'm assuming that.
Yeah, I don't think that the comparison so IQ games really is a solver for a problem, and contingency games are a problem, right? And so there is a version of IQ games where we've added logic for penalty, so for sort of logarithmic penalties to encode inequality constraints, and that version would also be capable to solve a feedback version of the contingency game.
I see. Thank you. Yeah, for IQ game, we can only apply those soft costs, right, in the cost function, but you cannot guarantee in the augmented Lagrangian form, right, to guarantee the constraint is satisfied. It's more like soft, not hard.
Yeah. So we didn't discuss the extension of IQ games to hard constraints, but it is in the code. So like there is it's effectively an interior point method where you add log penalties and you estimate the parameters of those penalties dynamically. So in that sense, IRQ games would be capable of handling constraints, I guess. Yeah.
Oh, okay. Thank you. Is that version of IQ games available, like adding the extra step, like the augmented step or the interpointed step you are mentioning?
Yeah, so it's available as code, but not in the paper. There is some really nice follow-up work on a closely related approach from Forest Lane, which you would find on his website, I think, which is on generalized feedback Nash computation of generalized feedback Nash equilibria, which is sort of the feedback version of the solution concept that we've used here. And that approach indeed would be directly applicable to contingency games.
Okay,
So,
yes, thanks. I will leave time for other people to ask questions here. Yeah, thank you.
Yeah, I also have one more question, and again about this branching time TB. Like a couple of questions already has been asked. Like if I'm correct, the current framework is agnostic to TB. It can be some hyperparameter, something like that. And you mentioned that work from Andrea, where we could, if I'm correct, we can update this TB like in a posterior manner, like do you think is this a posterior manner of updating of this branching time TB is the optimal one, or we could do some others ways of, I don't know, predicting this TB? What do you think?
so yeah, I mean, so maybe I should say what is the correct thing to do, which is technically to solve a partially observed stochastic game, which is kind of the game version of a POMDP. And in that setting, there's no real notion of a branching time. You just propagate the belief dynamics through the entire future. The main reason why we don't do that is that that's just hopelessly intractable. Like it's already intractable in the context of POMDPs, and it only gets worse in the context of games. I do think that there's so there may be so technically there's no fundamental reason why this formulation is limited to a single branching time. So you could kind of allow multiple branches in the future, and then it gets more sort of tree-like. I would be hesitant to claim, I mean, it's probably bold to claim that sort of fixing it to be in this posterior way is optimal. I don't think, yeah, I wouldn't think that is correct. I am currently not aware of any literature which characterizes this effect in theory. I do think so. That's certainly something that we plan for the extension, is to get a better idea of how good this approximation works in practice. So effectively, this TB, you can also see it as you simplify the belief dynamics as you have fixed uncertainty until TB, and then it collapses immediately, right? Whereas your true belief has some other dynamics. And so, yeah, figuring out whether there's maybe other tighter bounds would be important, because I would anticipate that the reachability approach in many cases dramatically over approximates the TB, so you get more conservative behavior that you would want to.
I see. So yeah, this is like coincides with my experience, and felt that this TB it also can be understood sort of timestamp for interactivity when we need to start this by some interactions. It's really one of the core questions and for the whole interactivity research. So probably it's hard to to directly incorporate it into some solution, and it's going to be some, I don't know, additional external research direction or something like that. Okay, thank you. Anyway, yeah, colleagues, any other questions?
Yeah. If nobody has other question, I have one more follow-up questions on the IRQ game and contingency games. So you said that for the constrained version of the IRQ game is equivalent to for the contingency game. So in terms of the solver perspective, so which one is more effective? My guess is the IRQ game will be more effective because it handles those dynamics naturally, right, without extra pain. But for contingency game, we treat it as the non-convex constraint, right? It's very hard to satisfy those inequality non-convex constraint. Am I right, or I'm missing some point about the contingency games?
Yeah. So again, I don't think that the comparison between ILQ games, which is a solver, and contingency games, which is a problem formulation, is quite accurate. So the thing that you would have to compare is the path solver and ILQ games. And I don't think so. I do agree that an experience ILQ games is quite quick, but these problems, they are not even the same. So ILQ games is solving a feedback Nash for a feedback Nash equilibrium, and here we are solving for an open loop Nash. And open loop Nash are sort of they're much less complex, so usually also much quicker to find. So I don't think that you can't claim that ILQ games would be faster. In fact, I don't think that this comparison makes a lot of sense. But for sort of a non-contingent game with a certain number of time steps and a fixed objective, both of these approaches, so an open loop solution and the IQ games type solution in the feedback sense, they could even look different. And there's no general study which says one of them is faster or not.
Okay, thank you. I maybe I need to read more about what's the difference between open loop and closed loop in the game things. But thanks for the explanation.
So if no more questions, so probably let's thank our speaker one more time. Thank you for your insightful talk.
Yeah, thank you for the invitation.
Yeah, it was really nice. And then let's finish. Bye, Lasse.
Bye.
Bye.
Thanks very much.